Welcome, everybody. Let's take a look at the next step in Newton's third law, which kind of builds on the action and reactions, and we'll go through some examples of those. But I want to take a look at masses and the role that they play in the effect that you would observe from an action or reaction. And then we'll use these ideas to build on the last lecture of this chapter, where we look at canceling forces and how rockets would fly and how you'd go about winning a tug of war and things of that nature. But I don't want to get too far into our last lecture and not give this one the credit and the time that it deserves. So let's begin. Here, got a little bit of review just to make sure that we're good with the action reaction statements. And maybe it's a good time to just review all of Newton's third law. A lot of times I'll just refer to it as action reaction. It's kind of the fast way of just saying Newton's third law, or rather than saying for every action there is an equal and opposite reaction, just action reaction is a little quicker way to describe it. Just like with Newton's second law, a lot of times we'll say FMA, for force equals mass times acceleration, or Newton's first law, we'll just say inertia rather than, the body in motion stays in motion unless acted upon by blah, 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 blah. So anyways, looking at Newton's third law with equal and opposite reactions, or we're going to go through some action-reaction statements here. So if I were to say a player kicks a football to the east, his foot exerts a force of 500 newtons on the ball. How could we write an action-reaction statement for this? You got to start with, again, an action. And it doesn't really matter if you pick the football or the foot. Just you got to pick one. And then you've got to ask yourself, okay, well, what else do I have? If it's foot and football, there's my other. Remember, these are forced pairs. The forces or the interactions, they're always going to happen in pairs, which, is a fancy way of saying two. Like if I'm playing cards and I got a pair of kings, that means I have two kings in my hand. Anyways, the forced pairs are just the two things that we're looking at that forces act on. Then we got to ask ourselves, well, how much force? And in this particular example, there's a numerical amount, right? We've got 500 newtons. And we got to ask ourselves what direction. So I chose his foot exerts a force of 500 newtons to the east on the ball. Now you might say, why did you assume it was a his? How come it wasn't a theirs? There's girls that could kick footballs as well. And I'd apologize. I'd be a little more gender neutral or less bias in my action statements here. I'll change that for next semester. But anyways, let's just look past my foolishness and say that our action statement is his foot exerts a force of 500 newtons to the east on the ball. So for your reaction statement, what you want to do, flip-flop the nouns, your person, place, or thing, and change the direction. With the force, it's equal. So we still keep that 500 newtons, right? There's no like calculation or something we've got to alter with that. So in this example, my reaction would be the ball exerts a force of 500 newtons to the west on his foot. So here's another example. We've got a book pushes down on a desk with a force of 25 newtons. So in my mind, I'm thinking, all right, well, what do I have? I got a book and I got a desk. All right. And I've got, something, the book pushing down with 25 newtons. So that means that the desk is going to have to push up with 25 newtons. How do I state that with an action and a reaction? Again, it doesn't really matter what you choose first for your action statement, by which I mean if you want to say the desk pushes up, but I usually try to grab what's out of the sentence here. So if this says a book pushes down, I'm going to say, all right, well, the book pushes down on the desk with 25 newtons. Basically just rephrase that. And then with my reaction, I'm going to switch the nouns. So I'll put the book where desk is and the desk where book is. And then I got to change the direction so that down would be coming up. In other words, my reaction statement for this is the desk pushes up on the book with 25 newtons. So if you're starting to get comfortable with this, you should be able to say, all right, if I read about a crane that exerts a force of 6,000 newtons up on a steel girder, steel girder is just a fancy way of saying like a steel beam, that it's lifting. Okay, so my action statement, I'm going to really kind of just repeat that. I'm going to say the crane exerts upward force of 6,000 newtons on steel. And then my reaction statement is the steel is going to exert a downward force of 6,000 newtons on a crane. So when we say equal and opposite or action reaction, I could say equal and opposite, I guess. Maybe that's a better way of just kind of referring to what Newton's third law is rather than the action reaction. But I think you're going to get comfortable enough where you know that action reaction has to be equal and opposite. And if you can always keep that in mind, you'll be in good shape. I am going to need you to understand, though, that when we always say equal and opposite, that's for the force and the amount and the direction, but not always the effect. Again, you might remember that example that I did with you on the video and the explanation with the calculations, where you've got a car and a bug. So if I'm driving down the street and car windshield hits a bug, there's an explosion, not of my car, but of the bug. So was that force equal and opposite? Yes, it was. But the effects were substantially different. That much force is enough to explode that bug. However, that much force, you wouldn't even be able to really notice the acceleration change to the car. So yes, it was equal. Yes, it was opposite, but that doesn't mean the effects would be the same. So last but not least, we've got a gun exerts a force of 1,000 newtons on a bullet when the bullet is fired. So our action statement, we can just kind of take a look at that, and then we can flip our nouns and change our direction, and we are good with our last action reaction statement. Oh my goodness gracious, I fibbed. There is one more. I apologize. But just for funsies here, let's take a look at the earth pulls down on an apple with a force of 5 newtons. Okay, Big Fat Liar Cash said we were done, but I got one more in me. I know the action statement is the earth pulls down on an apple with 5 newtons, so the apple pulls up on the earth with 5 newtons. Swap my nouns, kept the numerical value or the force the same, change the direction, bingo, bango, bongo. Action reactions, just that simple. So here's something to think about. If the forces are opposite and equal, why do we see the apple fall? Why don't we see the earth move up? If we're talking equality, and then just the direction that either the pull or the push changes, why is that? Hopefully you can think back to that little bug example and the car windshield that I gave you, and you know that it has to do with the mass. If we take a comparison of an apple and the earth, there's a huge difference in the amount of mass that we have there. There's a substantial amount more mass to the earth than there is just that apple. So that much force is going to have a greater effect on the apple than the earth. So same thing happens. If I jump as high as I can, push off as hard as I can, and I push down, does that mean that the earth pushes back on me? Yes. So would you see me jump? Yes. Would you see the earth move? Well, no. But does that mean that the earth doesn't move? No. It's just basically negligible. So long story short, those action reactions are going to be equal and opposite, but don't expect the effect to be the same. Now, if we looked at like the acceleration change, that's not going to be the same either, right? I mean, let's go back to the bug and the windshield. If I think of a car smashing into a bug, the acceleration of that bug, the change in speed was dramatic. It was just flying around, and then it basically changed to whatever speed that vehicle was going. Now, the car's perspective, in that interaction, when it hits that bug, would you expect to see much acceleration change there? No. And it's not because there was more force on the bug than the car. The force was equal and opposite. It's just that their masses were so different that the effects are therefore very much different. Oh, the Lions. Rough team to be loyal to, but we used to have a star kicker by the name of Jason Hansen, and he played for decades, and it seemed like forever, and you saw him trot out to kick threes more than you saw other people kick sevens. But anyways, I guess they'd be kicking the extra point for it to get the 7, but I digress here. Think of it like this. Why does the ball take off when this guy kicks the ball and the kicker stays still? If I'm saying that the force that's going to occur on that football is equal and opposite, hopefully you're at a spot where you're like, well, because that's a full-grown man. There's a lot of mass there. When he swings his foot through, that interaction between the foot and the ball, it's going to be equal and opposite, but the effects are different. Now, not today, but next time, we're going to start to look at, there's some other interactions that take place that could have an effect on this system. But for right now, I just want you kind of thinking, mass. Mass can play a role in what I would see as an effect. But if I'm just given a force pair, and I've got to talk about an interaction, it's equal and opposite. So a bullet and a gun, that's a good example, right? You know, we actually did an action-reaction with that. Think about how fast and how far a bullet goes when it's fired. Now, if you've never fired a rifle, they have what's referred to as recoil, or sometimes it's called kick. It's where the gun basically just kind of has a push back into your shoulder. What happens here? You've got an interaction between the bullet and the rifle. That force sends the bullet flying out of the rifle at a really high rate of speed. That force, when the bullet's fired, kicks the rifle back. But I wouldn't expect to see the rifle and the bullet take off at the same speeds. I know that there's going to be a big difference in what I would observe. So is that to say that the force was greater on the bullet? No, the force was equal and opposite. So remember, for this interaction, it's equal and opposite. So why do I see the bullet go flying so far? Think about it here. We've actually kind of got more than just the rifle. We've got the rifle and the guy holding it. So that's almost kind of like one thing. But even if we just look at the rifle and the bullet itself, the mass between those two things is so different, the effect is different, even though the force is the same. Here's a brief video to see some other killer examples of action-reaction.
Why do guns kick back when they're fired? How do rocket engines work? Why does the cue ball typically slow down when it hits a coloured ball, which speeds up? And why do I roll backwards when I throw a medicine ball forwards? Well, the answers to all these questions involve Newton's third law of motion. Newton's third law of motion is often stated as a little kind of rhyme. For every action, there is an equal and opposite reaction. What does that mean? It means that forces never, and I mean literally never, exist on their own. Newton's third law says that whenever an object, let's call it object A, exerts a force on object B, then object B exerts an equally sized force back on object A. Even though it's not always obvious, forces always come in pairs, which are called action-reaction pairs. In this lesson, we're going to look at Newton's third law of motion and how it helps explain a range of different phenomena. If I push this trolley, trolley A, into this trolley, trolley B, you can probably guess what's going to happen. Trolley B will experience a force that will accelerate it towards the right. Let's have a look. No surprises there. Trolley A provided a force on trolley B, which made it accelerate. However, there wasn't just one force acting, there were two. At the same time that A was exerting a force on B, which made B speed up, B was exerting a force on A in the opposite direction. So what happened to A as a result of this force? Well, it slowed down. As you can see, the dots are clearly closer together after the collision. Trolley B, the trolley being struck, doesn't even have to do anything. Just the fact that it's there and that a force is being exerted on it by trolley A means that it exerts a force back on trolley A. We can label the equally sized but opposite in direction action-reaction pair of forces at the moment of impact, FA on B and FB on A. And as usual, we've drawn the forces as if they're acting on the centre of mass of the trolleys. The same thing happens in this collision. Car A exerts a force on car B, which makes car B accelerate. But as it does, car B exerts in the opposite direction an equally sized force on car A, which makes it slow down. Of course, friction is also acting, but that's a different story. Now, the expression reaction force kind of implies that it comes after the action force. But in fact, the two forces, which are equal in size but act in the opposite direction to each other, occur at exactly the same time. Billiard ball collisions also involve Newton's third law. The cue ball exerts a force on the coloured ball, which speeds up, and at the same time, the coloured ball exerts a force back on the cue ball, which causes it to slow down. This process can occur any number of times in quick succession. The so-called Newton's cradle demonstrates this exact principle as well, as does this collision. Human A exerts a force on human B so that human B speeds up, and at the same time, human B, just by being there, exerts a force back on human A, which makes human A slow down. Now, even though the action force and the reaction force are always equal in size, the effect on the acceleration of each object varies depending on the mass of the objects that the forces act on. Let's go back to Newton's second law for a moment, F equals ma. For any given force, the acceleration of an object will be smaller when the mass is larger. If we rearrange the formula, we get A equals F over m. For example, if a force of 1 Newton is applied to a 2 kilogram mass, its acceleration will be 0.5 meters per second. But if a 1 Newton force is applied to a 100 kilogram mass, its acceleration will only be 0.01 meters per second. A given force...
Thanks for watching this short excerpt from episode 8 of the famous Shedding Light on Motion series, Newton's Third Law. If you're a teacher looking for an easy but effective way of teaching the topic of motion to your students, then visit our website to check out the series and to get hold of it. In this episode, Newton's Third Law, we look at that most poetic of all laws. For every action, there is an equal and opposite reaction. Newton's third law, in conjunction with Newton's other two laws of motion, can help us explain how rocket engines work, how our muscles work, why there's more to designing robots than just building motors, why guns kick back when they're fired, why we move backwards when we throw a ball forwards, and a whole lot more. You can read the full transcript of the program, complete with dozens of screen grabs, and download the worksheet that accompanies the program on our website. So visit us today.
All right, so lots of good examples there, right? But one thing that they made mention of that I just wanted to touch on is that when we say force pairs, that means there's two forces. Let's just say something's pushing down. Like if right now you're pushing down on your chair, then your chair is pushing up on you. Sometimes there's some confusion that like, well, it's one thing. No, it's a force pair. There's two forces. And then sometimes when we say, well, there's an action and a reaction, it does kind of paint it like, okay, well, this happens, then that happens. No, those forces happen at the same time. So while you're pushing down on your chair's pushing up on you. So yes, it's a force pair, but again, it's at the same time. So remember Newton's second law? The fellas touched on some examples there, and we looked at our calculations, and I think sometimes if you think about Newton's second law with FMA, the force and mass acceleration, and how that we've got force and acceleration proportional, but mass and acceleration are inversely proportional. Looking at that and kind of pulling it into this helps. So here's kind of some easy math, not really accurate math, but I just wanted to get the idea across with some easy numerical values. So let's just say that the force of this gun or this bullet being fired or this rifle firing the bullet, however you want to think of it, is 5 newtons. I get that's not accurate, but it's 5's a simple number to work with. And we're going to say that the bullet is a lot less than the gun. So we'll just say that the bullet's a kilogram. Again, not accurate at all. And the rifle little system here is 10 kilograms. So again, our numbers are make-believe, but just think it through. So mathematically here, if we're going to plug this in and I say, okay, well, if I've got force, the force here is, the same one that happens between the bullet and the rifle. I said 5 newtons. So if we're trying to figure out the acceleration change, how much speed does it change, right? And we take the force over the mass. So I said the force was 5 and the bullet was 1 kilogram. Again, not accurate, but if you crunch those numbers, 5 divided by 1, you wind up with 5 meters per second squared. That's the acceleration change, or the rate at which the speed changes. So if we said, all right, well, let's look at the rifle. Excuse me. The rifle's got, the same force that took place there, 5 newtons, equal and opposite, but it's pushing back in the opposite direction. And we're going to say, well, the rifle was 10 kilograms. So we take that same force, 5, and now we divide it by 10. I wound up with 0.5 meters per second squared. So can you see the acceleration on the larger mass mathematically? It's a lot less. The bullet went off flying at 5 meters per second squared. Acceleration, right? Again, not an accurate number, but you get the point. Where the rifle only changed its speed by 0.5, substantially less. So remember that mass and acceleration, they're inversely proportional. We talked about that before. We said that's a fancy way of saying the opposite's going to happen. If something's more massive, I'd expect to see less change in its speed. So we're not going to get too far into this today, but you think way back when we looked at like the contributions of Aristotle and then Copernicus and then Galileo and then finally we got into Newton. You might remember we said Galileo kind of dispelled some of Aristotle's thoughts of like there must be some force that's continuously pushing something around. Like if I throw a rock, there must be something that keeps it moving and then something that brings it to a stop. And Galileo got to a point where, and then eventually Newton. But anyways, now we know if I throw something, it'll continue in that direction at that speed forever unless some other force acts on it. So on Earth, we've got gravity or air resistance or whatever. But now in space, just to kind of think about that, if there was no force continuing a push on a bullet, it wouldn't be able to be fired. But you could fire a bullet in space because the interaction there happens between, in this case, the rifle and the bullet. So next time we're going to talk a little bit about rockets and how they work. And there's a common misconception that when we look at rockets, that the action-reaction statement that people would initially make would be, well, the rocket pushes on the air and the air pushes back on the rocket. And it turns out that the interaction, it's almost kind of like a gun that's continuously going off with a constant stream of bullets. And what I'm getting at here is it's actually the rocket and the exhaust. So that exhaust pushing on the rocket and the rocket pushing on the exhaust. That would be our action-reaction statement that we'd want to work for. So it turns out rockets can work in space. And even if there's no air for them to push on, because that action-reaction statement is going to be between the exhaust and the rocket, not the exhaust and the air. And actually, with no air, rockets fire a lot better outside of our atmosphere because that force air resistance is something that it's got to overcome to slow it down. So this is where you may have heard that we're considering, hopefully in the near future, getting like launch pads to the moon, where you could have that as like a jumping off point to like perhaps Mars or asteroids that we could mine or other places to colonize. But we'll get into that next time. If you've got questions, concerns, please reach out and ask. If you're good, I'm good. Until we meet again, take care.